Hi, this section is going to be sections 4.5.4 and 5 through 5.6 for chemistry 1151. So one type of a reaction we didn't cover in our last class was oxidation and reduction. It's a little more complicated to talk about this one, so that's why we left it for a separate video. For oxidation and reduction, we are looking for changing around of electrons. And so oxidation is the loss of electrons from an atom. I like to remember this as Leo. Losing electrons, oxidation. So Leo is losing electrons, oxidation. I like to think about that, Leo, as being like a little baby lion. Um, and a little baby lion has these really cute little paws, and this is for a reason, I promise. The paws mean that the baby lion is positive. So imagine that you're looking at a baby lion, it's cute, it's got cute little paws. That's a positive change, because if I lose negative electrons, overall, my substance is going to be getting more positive. So my substance gets more positive, gets more positive or positive. Then we talk about reduction. Reduction is the gaining of electrons. I like to think about reduction as GER, gaining electrons, reduction. Now, when we think about GER, we're going to think about Papa Lion getting upset that we're messing with his baby. So there's our lion teeth. So this is a negative interaction. So this is getting more negative. Because if we gain electrons, we gain negative electrons, we're going to get more negative. Okay, so whenever you have a loss of electrons, that's because someone else must be gaining electrons. This means that these two things happen together. So we call this an oxidation, or for short, redox reaction. So we always remember have two things. We always have something that's being oxidized, and you always have something that's being reduced. You cannot lose electrons unless someone else takes them from you, and you cannot gain electrons unless you took them from someone else. And so we're transferring electrons from one element to another in this type of reaction. So for example, we could have a zinc strip in a solution of copper ions. So we have copper ions and we have zinc metal. The zinc metal is neutral. The copper ions have a 2+ charge. What happens is that we're going to have a single replacement reaction. So the copper ions are going to turn into copper solid, and the zinc ions are going to turn zinc metal, zinc solid is going to turn into zinc ions. So zinc is going from zinc with no charge to zinc 2+ with the charge. So we got more positive. So that's Leo. Remember that that's more positive. So that means that it's oxidized. So if we get that O in Leo, that stands for oxidation. So we're looking at the changes here, the changes in the charge. Zinc was 0. Now zinc is +2. That's a positive change. So zinc must have been oxidized. And that means it lost electrons. How many electrons did we lose? Look at the charge. If I go from 0 to +2, that means I lost 2 electrons. If I go from 0 to +1, that means I lost 1 electron. Copper goes from +2 to 0. So we are losing those 2 electrons. We are getting more negative. So we consider that GER. And the R of GER stands for reduction. So we can tell what's being reduced because we're getting more negative. So you might see it written something like this. This is what we call a net ionic equation. The copper and the zinc are positive, but they're not just freely positive. There's another negative ion somewhere in there. It's just not participating in the reaction, so we don't put it. It's just kind of watching what's happening. We call it actually a spectator ion. This is a net ionic equation, which means we're only focused on the things that something is happening to. So let's say there's like some chloride in both of these sides, but it's not really doing anything. So we won't write it in all of our reactions. So just so you know, you might see reactions like this when we talk about oxidation and reduction. This is a fine reaction. It's called a net ionic reaction. Even though you may be a little confused as to how we can have just random things charged, you can't actually have something charged positive without having something charged negative near it. We're just not writing the negative part because it's the same on both sides. So we can see here zinc goes from 0 to +2. So that means we're getting more positive, which means we're Leo, which means we're oxidation, which means we're losing electrons. Copper goes from 2+ to 0. It got more negative, which means we're Gur, which means we're reduction, which means we're gaining electrons. So that train of thought is going to be what you need to figure out who's gaining, who's losing, who's oxidized, who's reducing. We can write these processes in what's called a half reaction, where we're actually showing the electrons. Now, we usually don't write electrons in chemical formulas because, as you can see, the electrons are a product and then they're a reactant. So they actually just cancel out, essentially. They get made and they get used. And so when we write full chemical reactions, we don't see the electrons, but we can actually pull them out into these things called half reactions to really get a sense of what is happening. So zinc is turning into zinc plus, and it's losing electrons as a product. So the electrons are going away as a product. Actually, these same two electrons are being grabbed by the copper ions and gained by them. So these two electrons are the same as these two electrons, but we have these little half reactions to really show us the electron being produced and lost in the oxidation, and the electron being used or gained in the reduction. The compound that is oxidized causes the other one to be reduced. So we call the thing that's being oxidized the reducing agent because it goes around reducing the other thing. It's the agent of reduction. So zinc is getting oxidized. That means it is losing electrons. So if zinc is losing electrons, what is it doing to copper? It's making copper gain electrons. So it is the reducing agent. It's the thing that is reducing the other substance. And then the copper, what is it doing to the zinc? It's oxidizing the zinc. So we call this the oxidizing agent. The agent of oxidation. So if it's the substance being oxidized, we call it the reducing agent. If it's the substance being reduced, we call it the oxidizing agent, because the agent part is telling us what is it doing to the other substance. These terms are a little bit strange. Just practice the best you can to try to remember that it's kind of the opposite. We just talked about this, but this is the copper is the oxidizing agent because it is essentially taking zinc's electrons, making zinc become oxidized. So here are just some examples of oxidation and reduction reactions. Notice that all of our oxidation reactions, the electrons are on the product side, meaning they're lost. And all our reduction reactions, the electrons are on the reactant side, they're being put in. So some examples you may see in the wild, I guess, is iron oxidizing. And so you see some iron, it starts to get rusty. That rust is actually iron 3 oxide. And so iron is neutral on the left side, and on the right side it has a +3 charge. So think about what happened to the iron. It went from 0 to +3. Was it getting more positive or getting more negative? If it's getting more positive, is that Leo or Gur? Right, that's Leo. So we're being oxidized. So the iron is getting oxidized, which means it would be the reducing agent. So iron gets oxidized, and we would call it the reducing agent. Same thing for oxygen. Oxygen starts as 0 and it goes to -2. Now, how do we know the charges just from looking at this? Or we got to remember how we talked about ionic compounds and breaking them down into their ions. So oxygen goes from 0 to -2. Is that getting more positive or getting more negative? That's getting more negative. Is getting more negative Leo or Ger? Getting more negative is Ger. Ger stands for reduction. So the oxygen is getting reduced, and the oxygen is the oxidizing agent. It's the thing that oxidizes the iron. So this is what we were just talking about. Another example of oxidation reduction reactions are batteries. And so here is a flashlight battery, specifically an alkaline battery, is a zinc and manganese dioxide. It's got some other stuff in it, but essentially the oxidation reduction reaction is the transfer of electrons that creates electricity. So we transfer electrons along the wire or the brass pin here, and that transfer of electrons causes electricity to be produced. And so we have oxidation happening in zinc, and then we have reduction happening in a manganese ion. The overall reaction would look like this. We're not going to talk about how to break this down into what's being oxidized and what's being reduced. What you can do is look at the charges. Zinc goes from 0 to +2. Manganese goes from +4 to +3. Now, sometimes we need to be able to tell oxidation reduction reactions, but we don't have ionic compounds. And so when we're talking about covalent compounds, we can also look at a couple of things to help us to figure out what's going on. If it gains oxygen atoms or loses hydrogen atoms, we say that it's oxidized. So how CH4, what happens to the carbon? The carbon loses hydrogen and gains oxygen. So if we follow the carbon, it loses hydrogen and gains oxygen. So the carbon substance was oxidized. And then oxygen is gaining hydrogen, right? And technically it's losing oxygen, right? O2 to O1, right? But it's gaining the hydrogen is really what we're looking at here. So that means that it's reduced. So we could say that CH4 would be our reducing agent. And O2 is reduced in our oxidizing agent. So remember, increasing oxygen or loss of hydrogen is oxidation, and reduction is loss of oxygen and or gain of hydrogen. And this is when we don't have ions to look at charges, right? We have covalent compounds that do this. So a connection to health, lithium-ion batteries in a pacemaker. The lithium is turning into lithium ion. And then in the battery, we have iodine turning into iodide ion. And so we have oxidation and reduction. The transfer of these two electrons is what powers the pacemaker. All right, so switching gears kind of completely, we're going to be going back to some conversion factors. I want you to remember as we talk about these conversion factors that you know how to do conversion factors. This is something that we've already done. So if you can solve something like how many kilograms in a gram or that kind of thing, then you can do these. It's just about memorizing a new set of conversions and then using them. So for example, if you know how to draw a car, sorry, not draw, if you know how to drive a car, and I just hand you keys to a different car, you can probably still drive that car. So just remember that you know how to do this. Just use the new conversions like you would use any equality. So a mole is a quantity that contains this many of a thing. So you could have a mole of eggs, you could have a mole of atoms, you could have a mole of molecules, you could have a mole of anything, and that's this many things. A mole is like a dozen, right? So a dozen, 1 dozen of something would be equal to 12. So a dozen eggs is 12 eggs. A dozen roses is 12 roses. So just like a dozen is 12 items, a mole is just a number of items. Now, the reason why this number is so big, and we can tell it's big because we have a positive exponent, is that we really are dealing with really, really large amounts of atoms in substances. And so if you're dealing with very large amounts of a substance, then we want to make sure that we're using Avogadro's number to count that. Because trying to count out individual atoms and molecules is pretty much impossible. We have this nice little package of a certain amount of them called a mole. So we call this number Avogadro's number after the person that came up with the idea of a mole. There's a video in D2L. If you just Google, if you Google TED Ed mole chemistry, there's a great little cartoon video that talks about just like what is a mole. It's kind of a hard thing to understand. So I think watching that video is worth your time just to get a good conceptual understanding. It's like a 3-minute video. I mean, it's a cute little cartoon, just so you can understand what we talk about when we say mole. So because a mole is a conversion factor, two things that are equal to each other, we can use it as a conversion factor in dimensional analysis. And so if 1 mole of a thing is equal to 6.022 times 10 to the 23rd of a thing, then we can put two things on top of each other in fractions like this. And so really we're just going to be doing the same thing that we've been doing with a new conversion factor. Make sure that when you're using Avogadro's number, that you're putting parentheses around your number in your calculator, or you're using the EE or EXP button in your calculator correctly. But if you're typing in like times 10 up 23, make sure you use parentheses in your calculation. So let's look at a sample problem. How many molecules are in 5.0 moles of carbon dioxide? So pause the video and see if you can work this out. I'll go through it when you're back. So first, our start would be this. Our unknown would be this. So what are we trying to find? Molecules. We're trying to find molecules. What are we given? Moles. It's the same substance, so we don't need to worry about changing substances, but if you want to write CO2 for both of them, you can. And so if we're starting with moles, we got to think about which one of these fractions we want to use. If we want moles to cancel, we're going to use this fraction because then moles cancel. The number, Avogadro's number, always goes with the particle. So molecules, atoms, or whatever. The mole is always 1. And then we just do our math. And they did it kind of weird. You just put it in the calculator and you'll get this. You want 2 sig figs. Your calculator's probably only going to give you 3. But make sure you give the correct number of significant figures. And then that's your answer. That's it. So don't make this harder than it has to be. If you don't know dimensional analysis, if you're struggling with that still, this is a time for you to make sure that you get help on that. But this is it for the Avogadro's number and mole conversions. Now, knowing how many moles something is and how many particles that is can be helpful and interesting, but really the most helpful thing for us, like in practical senses, is going to be how we can relate moles to mass. So we have something called the formula weight. We're going to call formula weight also molar mass. And it is the mass of 1 mole. And if it's in gram per mole, we call it molar mass. If it's in AMU, we call it formula weight. AMU is atomic mass unit. So if we want to know the formula weight for iron to sulfate, we would have 1 iron, 1 sulfur, 4 oxygen. Just look at the periodic table and add up all of those numbers, and we would get 151.91 AMU. Now we could write 159.91 gram per mole for the molar mass, and if you can see, if we have a per, right, that means we can write it as a conversion factor. So the molar mass is basically the formula mass, but in gram per mole. So the formula weight and the molar mass are the same number. The units are just different though. And so For example, if we have 12.01 gram per mole, we can say 1 mole of carbon is equal to 12.01 gram of carbon. And there, if we know if we have an equality, we can then turn it into a conversion factor. So if the molar mass of water is this, we can write it in these two ways. We can put moles on the top and grams on the bottom and vice versa. So let's try it. How many moles are in 100 grams of aspirin if the molar mass of aspirin is this? So we're looking for 100 grams of aspirin. That's my start. We want to know how many moles of aspirin. That's my unknown. Pause the video and try this problem and then come back. So if I'm trying to go from grams to moles, I want to get grams to go away. So I can either put grams on top or grams on the bottom. We'll choose grams on the bottom so we can get grams to be canceled. And then we'll get our answer. Just dividing will give us an answer. So this is nothing new, just new conversions, but I'm 100% positive that you can handle it. Now, if we want to do multiples, we want to go from grams all the way to molecules. This is showing you that you can kind of make a conversion factor that's a combination of both of these things. Like if a mole is this, we can just kind of, what they're doing is replacing this with that. I say don't need to do all of that, just do two conversions. So this will be our start, this question. And this would be your unknown. Why don't you pause and try this one and then come back when you're done. So first we have to convert milligrams to grams. We use a conversion factor like this, and then gram to mole. Now I would actually write it two ways. I would say 100.015 gram over 1 mole, or 1 mole over 180.015 gram. And I would use either the Avogadro's number. So make sure to not abbreviate molecules as moles, because those are very different. Or 1 mole over 6.022 times 10 to the 23 molecules. I would just use both instead of trying to make your own conversion factor. I mean, you can if you recognize that the mole is equal to Avogadro's number and you want to do a shortcut, you're welcome to do that. I think that for some people that might be confusing. And so just using the bare minimum like thought process here, just writing out what's the simplest way to think about this using multiple steps is maybe more convenient or maybe more understandable. So how would I write this out? 1,000 milligrams is a gram. Maybe you have a different conversion memorized for that. 180.15 gram per mole. And then I would have 1 mole is equal to Avogadro's number. And I abbreviate molecules sometimes as cules, and you can do that too. You see I have the same setup. I just did it out with things I don't have to think about making this conversion. I just do the two separate ones. And it, to me, I think is a lot easier to not have to do as much thinking to answer the problem. But pick whatever works for you. We're actually I'm going to move this to a different video. So we're done for now. See you in class.